In this video, we are going to move on from the concept of the unit circle to the so-called imaginary or complex numbers. I believe there's nothing particularly difficult about complex numbers if we start with our unit circle view and structure our program around it. Excuse the pun. I will reference the original works of Charles Steinmetz to explain why these complex imaginary numbers are closely tied to electromagnetism. In fact, it was in the eulogy following Steinmetz's death that a prominent academic remarked that Steinmetz essentially created electrical engineering out of the square root of -1, as noted by Eric Dollard. Just like the unit circle, the essence of complex numbers lies in moving and calculating vectors around 360 degrees. More specifically, it's about determining these rotating vectors and learning to calculate them using straightforward algebra. The best starting point is Steinmetz's description of the induction of electricity. Then let's quote Steinmetz from his Theoretical Elements of Electrical Engineering. Please refer to the accompanying image from his book and imagine the following. If a coil revolves with uniform velocity through a uniform magnetic field, the magnetism enclosed by the coil is expressed as phi multiplied by the cosine of phi, where phi represents the maximum magnetism enclosed by the coil, and phi represents the angle between the coil and its position of maximum enclosure of magnetism. Figure delta illustrates this concept. The electromotive force, or EMF, induced in the coil varies with the rate of change of phi multiplied by the cosine of phi and is expressed as E equals E subscript 0 multiplied by the sine of phi, where E subscript 0 is the maximum value of the electromotive force. This maximum value occurs when phi equals 90 degrees or at the position of 0 enclosure of magnetic flux. In an electrical circuit with resistance, R, and inductance, L, alternating current, I, interacts with these components in distinct ways. The key points to understand are: 1. Why lag is created. When an alternating current flows through a coil, it creates a changing magnetic field. This changing magnetic field induces a voltage called the counter-electromotive force, counter EMF, which opposes the current as per Lenz's law. The counter EMF is proportional to the rate of change of the current and reaches its peak when the current is changing most rapidly at its 0 point. Because of this opposition, the current takes time to catch up with the voltage, resulting in a phase lag of 90 degrees between the current and the counter EMF in a purely inductive circuit. I'm not going to go into every detail of this process, and we'll move straight to number 7. The most important takeaway from what we just explained is that there is, in our simple case, a 90-degree difference between the magnetic field phi and the induced electromotive force, or EMF. From image 7, we can also see that the current, denoted as I, is always in phase with the magnetic field phi. Meanwhile, the induced EMF lags behind the current by 90 degrees because it is proportional to the rate of change of the current, reaching its maximum when the current changes most rapidly. Depending on the circuit's setup, such as the inductance and resistance values, the situation becomes slightly more complex. The angle omega, shown in the image, represents the phase shift between the current and the total voltage applied to the circuit. This phase shift is determined by the circuit's resistance and reactance. The concept of the phase shift leads us to complex numbers. These numbers use simple algebra to combine resistance and reactance into a single entity called impedance, represented as a vector. Just like in our unit circle, the angle of this vector, called omega, helps electricians calculate the relationships between current, voltage, and impedance efficiently. So, how does this relate to our unit circle? Complex numbers allow us to treat these electrical quantities as rotating vectors, making calculations much easier and more intuitive for analyzing alternating current circuits. Now, if you haven't already, please go and watch my video in this playlist, which will also appear as a link at the very end of this video. That video is titled Unit Circle Explained with Values of Radians and How They Relate to Trigonometric Sine and Cosine. Make sure to pay attention to the fact that in our unit circle, the cosine function corresponds to the position of the first coordinate, just like the x-coordinate on the x and y axes. Similarly, the second coordinate corresponds to the sine function. This distinction is important. However, there is also a third main trigonometric function called tangent, which is related to the actual values or magnitudes of quantities like magnetism, electromotive force, and the so-called reactance. I will continue this series in a consistent way and revisit the ideas of impedance and reactance. Just as Steinmetz did, I will demonstrate how these concepts relate to Pythagorean ideas and trigonometry. This concludes part 1 of my video on complex numbers. Go watch the video on the unit circle if you haven't already. In the next part, we will build on what has already been discussed, starting with the definitions of sine, cosine, and tangent, using the hypotenuse, which is the length of the radius or clock hand in our case. Then we will explore the simple algebra of complex numbers, all in the spirit of the pioneering work of Charles Steinmetz.